basically finite state machines. State machines. And everything here is sort of relevant. Okay. State machine means it's fundamentally composed of states. Okay. And finite means it has a finite number of states. And that's very relevant because we like to build these things. Okay. You can't build things with infinite number of states. Okay. So in your mind, okay, think of a state machine as some kind of a central processing unit. Okay. And it has states. Q0, Q1, Q2, Q3, Q4, Q5, Q6, Q7. So in this example, I've drawn the central processing unit, my state machine with 7 states. And you can think of some kind of a needle, that can rotate around and sort of indicate what state am I in. So at any time I can sort of, ping my own state. I can say, what's my state? Okay, so and I just look at where's the needle pointing. So the needle goes round and round depending on, what stimuli I experience. And so where is the stimulus coming from? That's the input. Okay, so you can think that there's an input, and now, what's the input? Remember, we've formulated a computing problem as a language, and to solve the problem, the task is I give you an input string W, okay, and then you have to say yes or no, is it in the language? So, since we're building a machine, a very simple machine that solves computing problems, i.e. tests for membership in a language, the natural input is a string. In our case, we are focusing on binary strings. So the input is a string W, which is composed of ones and zeros and so on. 1, 1, 0, 1, 1, 1, 0, 0, just an example string. Okay. And so, if there's going to be an input to this central processing unit, then it must have some kind of a read head, okay, which can read the input. And so the idea here is that the read head will start somewhere, and typically we will say that it starts at the left, okay, and then it chomps up the first bit of the input, processes it. What does it mean to process it? Flips around and bumbles around and changes state like Mario. Okay. Then it chomps the next input and chomps the next input. And each time it chomps an input, it processes it, moves around, and then says, this is my current state. Okay. And it goes through the whole input, and then when it comes to the end, it's done, because there's nothing more to sort of, there's nothing more to do there. There are no more inputs to chomp up, to process. Okay. And so when it's done, it's in some state, in this case, for example, Q1. And then when it's done chomping up all the inputs, so we sort of, need some implicit way of telling the machine you're done with your input. So it tries to chomp and sees dirt. Okay. And at the end of chomping the input up, it has to output, yes or no. Okay. So it has to say what's my answer? Is my answer yes or no? And if the machine works, in other words, if it solves the problem, it'll only say yes when the string W is in your language, is in your problem, and it'll only say no when your string W is not in your language. Okay, so that's what it means to solve the problem. Now, okay, this is a nice picture to have, a central processing unit and so on and so forth. Okay, but we now need a more formal way to represent this machine. In particular, what does it mean to move around? Okay. Now we've understood how it processes the string. It just goes one by one through each bit, and we're going to leave the physical, the implementation details of that out of the theoretical discussion. Okay, so it processes the input string from left to right, one bit at a time, and when it comes to the end, it stops and says yes or no. So that part, we're going to take for granted, and we're going to focus on what's going on inside my machine, what's going on inside my central processing unit. Okay, so here's what's going on inside. Okay. Inside, it basically needs to have a set of instructions that tell it what to do for every bit that it chomps up, for every bit that it sees. Okay, and so there are a couple of things that we need to discuss. So the first thing is what are the states? The states. Okay. Second thing, what state do I start in? Because you gotta I need to know where to start myself, so I'm born. Okay, what state am I born in? What state do I start in? What are the states? What state do I start in? Okay. What are my instructions? So how do I move around? How do I change states depending on the bits that I see? Okay. How do I change states? And then, once I'm done with the input string, once there are no more bits, okay, how do I decide yes or no? How do I decide yes or no? So let's discuss all of these things. Okay, so in this example, what are the states? Okay, there are 7 states, but let's take a much simpler example to illustrate. So let's imagine a finite state machine with 3 states. So I have a state. Typically, we start labeling the states Q0, Q1, Q2. Now you can label the states any way you want. Okay, and in general, when we build these machines, we try to label the states to sort of indicate what the state means, and that will become clear as we do more and more examples. Okay, but the most abstract way to label states, the sort of simplest way to label states, is just like we're labeling a graph. We label the vertices v1, v2, v3 up to vn. So we have states q0, q1, q2. Okay, and let us agree that the state labeled q0 will typically always be the start state. That's why we say 0 for that. Okay, at time 0, at bit 0, I'm in state q0. Now, normally we will indicate that with some kind of an arrow. Okay, to indicate that that's where you start. So these are my states. Okay, so I've told you the states and what state I start in. Now, how do I change states? Now, the most beautiful way to represent, the mechanics of changing states, what you can think of as, what are my machine instructions? What's the instruction set that I'm going to operate with respect to? What's the instruction set that I'm going to use? Okay, the most beautiful way of representing the machine's instruction set is using a directed graph. Okay, so we put these states as vertices in a graph. Q0, Q1, Q2. Okay, and now what I need to do is I need to tell the machine, how to change state. So which state you go into depending on what state you're in and what bit did you read. Okay, what bit did you chomp? Okay, so this is the start state. This is the, state 1, state 2, and we'll indicate the start state with an arrow. Okay, and then, what I'll say is that if you see a 0, so I'll indicate that with an arrow from the start state. So when you start and if you see a 0, go to state Q1. Okay. If you see a 1, please go to state Q2. Okay. Okay. And now if I wanted to be very formal about this, I would actually write out the instruction set, because we can't really represent pictures in a computer, but an instruction set that's well written out we can. So instruction set, or we can call it machine instructions. Okay, so what does this, so each arrow here corresponds to 2 instructions. What this says is, if you're in state Q0, okay, and you see the bit 0, then please transition to state Q1. Okay, so a machine instruction is just a triple. What's your current state? What did you see? Where do you go? Okay, so here, what's this instruction? 1, 2, 3, do it. Okay, and now I'm going to tell you, it's the instruction, if you're in states Q0 and you see a 1, then transition to Q2. Okay, and so I'm going to now draw all the instructions, because I have to tell the machine what to do in every state and for every bit that it could see. So in state 1, if you see 0, please continue to stay in state 0. If you see a 1, transition to state Q2. Okay, and in state Q2, if you see a 0, please transition back to Q2. If you also see a 1, please transition back to state Q2. So to sort of avoid having to rewrite that same arrow twice, I will put a 0 and a 1 as the labels of this arrow. So that means that, if you see a 0 or a 1, you stay in Q2. Okay, so let's write out all those instructions. So here, if you're in Q1 and you see a 0, stay in Q1. If you're in Q1 and you see a 1, move to Q2. If you're in Q2, okay, and you see a 0, stay in Q2. If you're in Q2 and you see a 1, stay in Q2. There. Okay. So, how do I change states? You can specify machine instructions. If you don't want to draw stuff. Okay, but this is ugly. We don't know what's going on here. But when we look at this, look at how beautiful it is. So we can specify the mechanics of how my finite state machine is operating using a directed graph of this form. We call this, the state transition diagram. Machine instructions. Okay? State transition diagram. State transition diagram. or graph. Graph for the obvious reason that it is indeed a directed graph. One of the most beautiful applications of directed graphs is to sort of represent models of computing. Okay. Now, okay, let me tell you, how do I change state? So first, in order to specify how you change states, I have to specify your instruction set. And now I'm going to now tell you how we use this instruction set in order to change states. So the process is very simple. Step one, okay, so how does the machine operate? Machine operating instructions. Okay. Start in the start state. Start in the start state. Okay. Q0. Okay. Now, process bits from your string one by one. 2. Process bits from the string, input string, one by one. Okay, so you'll process input bits, one by one. Okay, and for each input bit, follow the corresponding instruction depending on your current state. Okay, and what the bit is. For each input bit, follow the instruction for the current state and bit. Okay. And now, when you're done with bits, when no more bits, when there are no more bits, you've arrived at your final state, at your resting state. So this means that you are at your resting state. Okay. So you're done with the computation. Now all you need to do is output yes or no. Okay. And so what we're going to do is we're going to ask you, when you specify states, to also tell me which states are yes states and which states are no states. That's the final ingredient in the automaton, which is to tell me how to say yes or no. So determine, say yes, if your resting state is a yes state, and no, if the resting state is a no state. Okay. So when I specify the states, I need to tell you what are the yes states and what are the no states. So we need a sort of a notation for that. So, now if we were in black and white, the notation would be you place sort of a double circle around the yes state. So this is the yes state. That indicates the yes state. Okay, in this particular example, the starting state is a no state, and the state Q2 is a no state. Okay. Now, just once, I will show you what it looks like in the book with color. What we do, just to emphasize that this is a yes state, is we also color it green to indicate, wow, this is a yes state. Look at my beautiful coloring abilities, green. Put a little bit of nice, green. Okay. And so if I do that in this picture as well, so now in black and white, and the simplest way to do it is to just say, okay, here, double circle. That indicates that it's a yes state, but let's get all fancy and color beautifully color. We need to have time lapse so that you can see time lapse coloring. And then you will learn how to do coloring of finite automaton states. Look at how beautiful it is, soothing. Okay, there. Okay, so let's do an example. Okay, let's do a bunch of examples. So let's start with this machine and let's see what does it do with the input string 0, 1, 0. Okay. So now, one way to sort of represent the start of the computation, and so this is sometimes called the state of the machine. Okay, so we have the machine. Okay, so the machine is starting in state Q0. So we have the machine starts in state Q0. Okay, starts in state Q0, and I'll put a line here to just indicate that that's its state, and a read head. So it has a read head. Okay, so the read head, where is the read head? Is at 0. Okay, and then the rest of the string is also still there. Okay, so this is one way to represent sort of the configuration of the machine. Okay, and now let's follow the instructions. Okay, so what's the first thing it does? It reads in the 0. So it reads in the 0 from state Q0. It reads in the 0 and goes to Q1. So we would say that, under the influence of the machine. Okay, so let's give this guy a name. Let's call it M. Okay, so under the influence of the machine, this configuration, after it chomps up 0, okay, will be state Q1. Okay, so it goes from 0, it sees the 0, goes from Q0 to Q1. Okay, and it's processed the 0, and so now its read head is ready to process the 1, and then there's the bit 0 afterwards. Okay, so that's just a little bit of notation that allows us to keep track of what the machine is doing. Start in state Q0, ready to process bit 0. Okay, and by the way, there are some other bits remaining. Okay, so we processed bit 0, so that means that it's now on the left of the read head. Okay, so the read head has moved one step to the right. So I'm ready to process bit 1, and I'm in state Q1. Okay, so I'm in state Q1, I process bit 1, I go to state Q2. So under the influence of the machine, I go to state Q2, I've processed 0 and 1, and I'm now ready to read bit 0, and there's nothing after that, okay? And then under the influence of the machine, I'm in state Q2, I process the 0, I stay in state Q2, so I stay in state Q2, okay? And now I've processed 0, 1, 0, and my read head is positioned at a spot where there are no more bits. I'm done. Okay? And then I look, Q2 is not a green state. It's not an accept state. Now, usually we won't have the green. We'll just have the double circle. It's not an accept state, so I say no. Okay, so this gives me no. Okay, so pop quizzes, exercises. Okay, give the trace. So that we call this the trace of the computation. Give the trace for the following inputs: epsilon 0, 0, 0, 0, 1, 1. Okay, pause the video, 1, 2, 3, 4, 5. Okay, now if you're coming back, okay, you should have said epsilon is, the answer is no. Okay, so this is no, no, yes, no. Okay, now I'm going to give you a harder exercise. Okay, so I'm going to show you, so at any time we can tell you what the configuration of the machine is, and you can continue the computation. For example, here the configuration is, I'm in state Q2, and I'm going to see 0, 1, and then I've already processed 0, 1, and what's remaining is 0 and nothing else, and I'm currently reading 0. So I'm going to give you some configurations, and you are supposed to continue the computation and tell me yes or no. So here's the configuration. Q0. Okay, you've processed some bits, and now here's the twist. I'm not going to tell you what you've processed, but your configuration is 0, 0, 0. Okay, so you have remaining 0, 0, 0. And then you're in, let's say Q0, Q1, and you've processed some bits, and I'm not going to tell you what you've processed, and you're next, you're positioned to read 0, 1, 0. So these are interesting. You say, well, but these configurations are there. You can think of them as partial configurations. Okay, and pause the video and see whether you can identify what's the final answer, yes or no. In the meanwhile, I'm going to erase the machine's operating instructions. Okay, and you pause the video 1, 2, 3, 4, 5, and you're coming back, and here you should have said yes. Here, you should have said no.
Okay, and this is a very important property that I'm illustrating here. We'll use it again later. Okay, but you might be saying, oh, but wait a minute, you didn't tell me the full configuration. How can I solve this problem? And that's the beauty of the finite state machine. Okay, the beauty of the finite state machine is if I tell you my current state and what's coming, I don't need to know how you got to the current state. So let's see this in action. I'm in Q0. I don't care what's happening here. I'm about to read the 0. So I'm in Q0. I'm about to read the 0. Okay. In fact, we could have deduced that, if you're in Q0, you haven't processed anything yet. But you're in Q0, you're about to read the 0. So you read the 0, you come to Q1. And then you'll read another 0, you'll stay in Q1. Another 0, you'll stay in Q1, and you'll say yes. Okay? Here you're in state Q1. You don't care how you got there. And you're about to read a 0. So you stay in Q1. Then you read a 1. Then you move to Q2. Then you read a 0. Then you stay in Q2. And you say no. Okay? So, important. In a finite state machine, if you know your state and the future bits to come, you don't care. You can say yes or no without knowing, okay, the previous bits. In other words, you don't need to know how you got to the state Q0 or Q1. You don't need to know how. You can immediately say yes or no. Okay, so that's important. All right. So now, when we're talking about these type of computing machines, there are sort of two questions that we would like to ask. Okay, so the first question is, so here's a computing machine, right? What problem does it solve? So effectively what I'm asking is, for what strings does it say yes? Okay, so let me erase this. For what strings, for what input strings does M say yes? Okay, you can think of that as the yes set of M. We call that the language or the problem that's solved by M. So we say that the language of M, the problem that's solved by M, the language corresponding to M is exactly this yes set, is the strings for which M says yes. Okay, so now if I ask you what's the yes set for this, we're really typically just asking you for a description of this yes set. Now we have various ways to describe it. We can use variables, we can use regular expressions, we can use recursive definitions, but in general, the first step is to come up with an English description. So let's look what happens in this machine. Okay, you start at Q0. If nothing comes, so if your input string is epsilon, you stay here forever, you're done. Okay, and you reject. You say no. Sometimes we say yes means accept, no means reject. Okay, so you say no, reject. Okay, and if a 0 pops, then you say you sort of go into the accept state, and you're waiting. And if as long as more zeros come, you will remain in this accept state, this yes state, and you will say yes. The moment you see a 1 from either Q0 or Q1, you move into this kind of this kind of black hole state, this kind of sink state from which you can never escape, because whether you get a 0 or 1, you will always stay here. And what brought you here is a 1. So if the string starts with a 1, you're done. You will never escape from this reject state or no state. If you get into the accept state but then ever see a 1, you will reject. So basically this machine is rejecting or saying no to any string that has a 1. Okay? And also it's rejecting the empty string. So it accepts all strings with a non-zero number of zeros and only zeros. So the language of M in this case is strings with only zeros and at least 1. At least 1. Okay, so it's the language is 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, and so on. Strings with only zeros. So we could, if we wanted to use sort of set and variable notation, they're the strings W, where W is equal to 0, concatenated, raised to the concatenated power n, where n is greater equal to 1. Okay, so we figured out the language that is sort of, we say that this language, this problem is solved by M. We say that's the language that's accepted by M. The language of yes strings for my machine M. Okay, now, you can get lots of practice with this type of question. So, question. I give you a machine M and I ask, what is L of M? What is the language that it solves? Okay, so I give you a machine M and I ask you what's the language that it solves. And exercise 24.2. Lots of practice with this, and get that practice, okay? Because these are very important machines, okay? Finite automata. So I give you a machine, just like here, and I say, what's the language it solves? So we go through exactly this kind of an exercise. The other kind of question we like to solve, and this is the one we are more interested in, is I give you a problem, I give you a language. Question. I give you a problem. i.e., now we know what a problem is, what a computing problem is, i.e. a language, L, and I ask you to construct a machine that solves that problem. Okay, so what I'm asking is, can you construct a finite state machine, like this, okay, and we typically will represent them with these transition diagrams. So can you construct a finite state machine for which the yes set is exactly that language? And anything that's not in that language, the machine will say no. Okay, so that's what we're going to discuss next, and we're going to do, we're going to discuss it through examples. Okay, so I give you a problem, i.e. a language L, okay, and I ask, can you find a machine M for which, the problem solved by M, so L of M is equal to L. Okay, so that's the question. Okay. In other words, designing a finite state automaton, designing DFA, sometimes we call this a deterministic finite automaton, or DFA, or finite state machine, finite automaton, designing an automaton to solve a particular problem. Let's talk about that. So let's erase.